Okay, we're using computer audio. Let's see, I think in this class at least, the tests are already up because in this class everybody managed to submit them correctly to the anyway, to the turn-in site for it. And hopefully all of you have looked at those by now. Or do you get a notice about that when I grade them? I'm just curious.
Yeah, you get an email and
Okay.
a little notification on the Canvas sidebar.
Oh, okay, good. All right. Well, let's see. Today we're continuing on with special relativity stuff. I just posted an assignment that's really over the stuff we did last Thursday and the things we'll be doing today, but it's not due until Friday. And then by then we'll be looking at some other things that'll be on the last homework assignment for the quarter. And I may have that posted by Friday as well. I don't think you'll find any of the questions or problems on this week's homework particularly difficult, hopefully. So you should be able to do those okay. Let's see. I think I'll switch over to the visualizer. And I don't remember if Thursday, if we finished this problem off, or did we just get partway into the binomial expansion and have to stop? No, you can't see the top of the problem, but we have the rest radius of the Earth. And this is a problem looking at how the moving lengths appear shortened along the direction of motion. So it's dealing with length contraction, but it's a very small length contraction. So you have to track down a working pen. Okay, this one should work. Sort of, a little too fine, but that's okay. All right, anyway, the rest length of the Earth is 1,240 or 12,740 kilometers. And the shrunken length that a moving observer would see, or someone who's moving with respect to the Earth, or for whom the Earth is moving with respect to them, and it turns out it doesn't make any difference which it is, but they'll see the rest length divided by gamma. And so we need to figure out what that is. But if you try to calculate gamma for this one, you're not going to do very well because your calculator will just tell you it's 1.000 something or other. But what we're interested in is the difference between the rest length and the length that an observer would see. So we just want to know by how much would the diameter appear to be shortened. Okay, well, that's going to be the d minus d prime here. And so I went through this a little bit, and then we had the approximation, but I don't remember, did we actually calculate this number or not?
I think we did.
We did. Okay, how much was it shortened by?
6.28 centimeters on my paper.
Okay. Yeah, so d minus d prime, 6.28 centimeters. Okay, I must have tossed that piece of paper. That's all right. Okay, so out of 12,740 kilometers, this is the amount that it's shortened by, which isn't very much. And so I hope you kind of got the hang of the binomial expansion. I think we'll do another problem or two that involves this today. So by then you should be somewhat familiar with it. And we'll just move on from there. Okay, the next problem on this batch is a more extreme example. Suppose a spaceship flies past the Earth at 0.99 C. To occupants of the spacecraft, how will the Earth appear? And try to make an accurate drawing. Okay, well, we can try to make that, but first, let's figure out, we'll just draw a circle representing the Earth, and then kind of do a calculation here to figure out how much it appears shortened by. And we'll imagine that there's a spaceship that's flying by here, and even though anything that's going to be going at relativistic velocities probably isn't going to have some big cone on the back to shoot projectiles out of, it's going to have to do something else. But this thing is moving with respect to the Earth at 0.99 C. Now, we have our regular diameter of the Earth, so that's the 12,740 kilometers. And that's what it would ordinarily or look like to someone who's not moving at an extremely high speed with respect to it. But then they will see a shortened length, and for them, they'll see a diameter of the Earth prime, which is going to equal the rest diameter of the Earth divided by gamma. And so that's the shortening, but it's only along the direction of motion that it appears shortened, not perpendicular to the direction of motion. And so it'll be shrunk in this direction, but not in this direction. So that's kind of a weird thing that happens. Well, with the speed equaling 0.99 C, we can get a reasonable value for gamma on this thing. So gamma is going to be 1 over the square root of 1 minus, now I'll just do this again. This is usually V squared over C squared, or V over C squared. But in this case, V over C is going to be 0.99 C divided by C. So it's just going to be 0.99. And I mentioned last week that often that ratio is just written as a Greek letter beta. So in this case, beta is 0.99. So we'll have that thing squared. Then we can calculate how much it's shrunk by. Where am I? Where's a run? 1 divided by square root of when I was taking a course in special relativity at Eastern, they had a quarter-long course where we did all kinds of stuff, but I had my very first programmable calculator then, and I just programmed into it calculating gamma. All I'd have to do is input the speed, but this isn't that much work. I get about 7 point, how many significant figures do we have? Not that many. 7.1 is about the value of gamma. So if I measure this length and divide it by 7, that'll be the new apparent length. Oh, that one doesn't, here we go. I wanted something with millimeters on it. It's going to be about 79 divided by that number. Which should be around 11. Yeah, for practical purposes, it's only going to be 11 wide here. And so if I just stick in an 11 millimeter long line there, this is approximately what the Earth is going to look like to that person. So instead of being a sphere, it's going to be a pancake, more or less. So that's what they would appear to see. So the universe would look much different if you were traveling at a large fraction of the speed of light. And all lengths are going to appear shortened like this along the direction of motion. So that's kind of fun. Well, maybe you could do something with this. Assume the distance to the galactic center is 27,000 light years, which it is. That's approximately what it is. Sometimes you'll see 28,000 light years. Sometimes it'll be rounded to 30,000 light years, but that's a good enough approximation anyway. Can a person, in principle, travel from Earth to the center of the galaxy in a normal lifetime? Explain either from a time dilation or a length contraction argument. Well, time dilation wise, the time dilation ends up being, let's see, moving clocks run slow, so the delta t prime is going to be gamma delta t. Now, in this case, we'd be interested in perhaps a proper time interval. We might be interested in the delta t. This might be the time that passes for the person on the spaceship. An observer who watches that spaceship moving away from them would be measuring the delta t prime. And so this spaceship's going to have to go pretty darn close to the speed of light. And so if they're going close to the speed of light, an observer here on Earth watching that spaceship move away, and if they had the patience for it or could somehow live long enough, they'd think, oh, it took 27,000 years to get to the center of the Milky Way galaxy. By the way, that LY, I didn't state this, but it stands for light years. And that's, this is expressing a distance as rate time. The time is in years and the rate is the speed of light. So those algebra students who struggle with this concept may really struggle with this concept. I don't know. Anyway, can you in principle travel from the Earth to the center of the galaxy in a normal lifetime? Well, if you have a big enough value of gamma, you could. And let's see, what constant speed would be needed to make this trip in 29 years? That would be the proper time. So delta t is going to equal 29 years. Delta t prime is going to be about 27,000 years, because this thing's going to be going very close to the speed of light. So we can figure out what that happens to be. And actually, the 27,000 light years is approximate anyway, so that works out. So gamma is going to be 27,000 divided by 29, which is something or other. And we would get 931. Okay, well, gamma is equal to 1 over the square root of 1 minus beta squared. And I'm going to set this equal to that and solve for beta in terms of gamma, because we may end up doing this a few times, and it would just be nice to not have to do that every time. Although I'll probably lose the piece of paper I put this on, unless I tape it on the wall in front of me. That would be a good idea. Let's see, I've already got a few holes on that wall. So square both sides and I would get gamma squared is 1 over 1 minus beta squared. Think of that over 1. Cross multiply, and I would have, no, I don't want to cross multiply. I'll just flip both fractions. 1 over gamma squared is going to be 1 minus beta squared. Beta squared will equal 1 minus 1 over gamma squared, and beta will equal the square root of 1 minus 1 over gamma squared. Okay, so we can do this. Gamma was 931. Yep. Okay, so oops, guess it didn't need to go that far. We might almost need to do a series expansion on this thing, or could. Yep. I get 1.000. Okay, because it's going to have to be going so close to the speed of light. So my power series expansion again, 1 minus 1 over gamma squared. If I think of this as, need scratch paper, not real paper. I don't want to mess up my other stuff. Oops, except I did want that series expansion. 1 plus x to the n is 1 plus nx plus, okay. By the way, do any of you ever watch Veritasium? I stumbled across one of those where I can't remember, Derek Muller or something like that is the guy's name who's on there, but he showed how Newton used the binomial expansion to figure out a better way to calculate pi. Used to be, up until that time, everybody had calculated pi by taking a circle and putting inside of it a regular polygon. And they'd done it with more polygons with more and more facets or edges to them over the years, over the millennia, actually. And then Newton came along and figured out a way to do it with a handful of calculations and get more precise results. So it's kind of a neat thing. So I don't remember exactly what it's called, but anyway, it's using a series expansion to do that. So there's our series expansion. And let's see if we can do it for a value of this thing that's going to be very small. So in our case, our x is going to equal 1 over gamma squared. Our n is going to equal 1/2. And actually, it's going to be minus 1 over gamma squared is what our x is going to be. So for our series expansion, we'll have 1 plus x, or 1 plus, we'll have the square root of 1 minus 1 over gamma squared is going to equal 1 plus n is 1/2, and our, it's just x on this first term, minus 1 over gamma squared. And then, let's see, the next term in the expansion would be 1/2 times minus 1/2, 1 minus 1/2, or no, it's 1/2 minus 1 is minus 1/2, times minus 1 over gamma squared divided by 2 factorial, which is 2. And this ends up being 1 minus 1/8, I guess. So let's figure out what this thing ends up being. Is this going to get me anywhere? I'm not sure. Actually, I'm going to look farther. I'm just going to change the mode on my calculator to show more digits. then I'll be sorry I did, but okay, well, I get about 0.9994231. A whole bunch of nines strung together here. Yeah, well, in principle, if you were going at that fraction of the speed of light, you could do it. You could make it in 29 years of proper time, but back on Earth, 27,000 years would expand. I don't feel like carrying out this any farther right now because it's not going to be all that useful in this case, I don't think. I would have, let's see, 1 plus my first two terms are probably going to yield a number very similar to that. Oops, I want a minus sign. 1 divided by how'd I do? Oh, just the first two terms of this give me the very same value that I have right here. And so that's nice to know. No point in doing any farther ones out, but this one's not all that instructive doing it with that. Although if we were going much faster, we'd probably run out of space on our calculator for the digits that would tell us anything. So, okay, that was not all that useful. But this one we might actually have to use the series expansion on. I thought there were some other ones, maybe not. That one, that one. Okay, a fighter jet flying at 686 meters per second, which is roughly Mach 2. By what fraction would such a jet appear to be shortened in length according to an observer at rest? Now, the fraction it would be shortened in length is going to be its, we'll have L, which is going to be the proper length. L prime is the relativistically shortened length, which is L divided by gamma. And we want the fraction it would appear to be shortened in length. Well, the amount that it appears shortened in length is L minus L prime. The fraction is if I divide that by the ordinary length. Sometimes we'll put a subscript of 0 on the proper length. I'm just leaving it without a prime on there. And this ends up being 1 minus L prime over L. But L prime is L over gamma, so this is 1 minus, that's supposed to be an L, L over gamma divided by L. This ends up being 1 minus 1 over gamma is what it happens to be. So in this case, gamma is going to be very close to 1 because it's not going all that fast. And let's see, can I do anything with this? Oh, here I was solving for the fraction of the speed of light that it was going. In this case, gamma is going to equal 1 over the square root of 1 minus v squared over c squared. 1 over gamma is going to equal the reciprocal of this, the square root of 1 minus v squared over c squared, or beta squared. We could leave it as v over c, I guess. And we want 1 minus 1 over gamma. So that will work. I think. let's see what happens. We'll just plow ahead with this thing and see if it works. Okay, the square root of 1 minus, I'll call it beta squared so I don't have to write so much. Using the series expansion on here, and I will get 1 plus. Now my n is 1/2. My x is minus beta squared, which is going to be pretty darn small in this case. For me, beta is going to equal 686 meters per second divided by 3.00 times 10 to the 8th meters per second, to 3 significant figures. And it's about 2.29 times 10 to the minus 6th. Okay, now that's going to be squared here, so it's going to be around 5 times 10 to the minus 12th, which is pretty darn small. The next term in the expansion is the one that would have beta squared squared, so it would be this thing to the 4th power, which is going to get you to 10 to the minus 24th, which is about 12 orders of magnitude smaller than this. And so this is a good enough approximation here. So our fractional change in length, L minus L prime over L, which is 1 minus the square root of 1 minus beta squared, because it's 1 divided by gamma, is going to end up being, whoops, I should have said, oh, I did some monkeying around here. This is 1 over gamma. That's not equal to gamma. Okay, anyway, 1 minus that thing, which is going to be 1 minus 1 minus 1/2 beta squared, which is just 1 minus 1 is 0, minus and a minus is a plus. It's just going to be 1/2 beta squared. That's going to be the fraction that it appears shortened in length, which is going to be 1/2 times this thing squared, 2.29 times 10 to the minus 6th squared. And this is a dimensionless quantity because it's V over C. So, oh, I got to get rid of all these significant figures on my calculator. They're not significant, is the problem. Okay, the fraction it appears shortened in length, L minus L prime over L, is about 2.61, not that it's important to have significant figures on here, times 10 to the minus 12th. So around 3 parts in a trillion, I guess. So not that important. Okay, how long would the plane have to fly at this speed before the pilot's watch would differ from a watch at rest by 1.00 seconds? Oh boy, okay, here we go. Need scratch paper for this, or more, anyway. Here's a good one, the track of Mars from May to December 2003. Probably won't need that one again. Okay, well, our length contraction is that the delta T prime is going to be gamma delta T. Okay, now here's the proper time measured on the pilot's watch. Here's the time that an observer on Earth would say passed. According to this, let's see, we didn't exactly figure out gamma, but we kind of did. But it says before the pilot's watch. Okay, the pilot's going to be the moving thing in this case. Let's see. Yeah, and it will differ from a watch at rest by 1.00 seconds. So this is the watch at rest. And this will be the pilot's watch, I guess. Let's see. These things are hard to wrap your head around. The observer is going to say the pilot's watch runs slow, or the observer on the Earth, because the pilot is moving very fast. Yeah, I'm going to call this the pilot's watch. That's the thing that's moving, but it's a proper time measured in the pilot's reference frame. This is the observer's watch. Okay. And we'll have that delta t prime minus delta t is going to equal 1.00 seconds. Okay, well, delta t prime is gamma delta t. So gamma delta t minus delta t is going to equal 1.00 seconds. And it's delta t that we're after. So now the delta t is actually going to be a time on the pilot's watch, but I suspect, well, when we get to the end of it, all we'll have to do is just add 1 second to it, and we'll have the time on the earthbound observer's watch, if it's going to make a difference. So delta t times gamma minus 1 has to equal 1.00 seconds, or gamma or delta t is going to have to be 1.00 seconds divided by gamma minus 1. So in this case, we're going to have to do a series expansion on gamma, because gamma is going to be so close to 1 that our calculator isn't going to help us at all in this case. But we can expand gamma minus 1 to the minus 1. Or let's see, since, yeah, I can do that. 1 over the square root of 1 minus beta squared minus 1 is going to equal to the minus 1. That will equal 1 over the square root of 1 minus beta squared minus the square root of 1 minus beta squared over the square root of 1 minus beta squared to the minus 1. Got a common denominator there, and I will have 1 minus the square root of 1 minus beta squared over the square root of 1 minus beta squared to the minus 1. This may be kind of messy. I'm not so crazy about this. Maybe just doing the gamma minus 1, expanding that. This is looking messy. So gamma minus 1. Expanding gamma, we found out that when you have pretty low speeds, I'll be expanding 1 minus beta squared to the minus 1/2 minus 1, because gamma is 1 over the square root of 1 minus beta squared, which is that. Anyway, so do our expansion on this thing. N in this case is minus 1/2. So this will equal 1. plus a minus 1/2 times x, which is minus beta squared. And then I'm subtracting 1 from that, and I end up with 1/2 beta squared again. Because 1 minus 1 is 0. So that's what my gamma minus 1 ends up being, wherever it went. Here we go. So it'll just be 1.00 seconds divided by 1/2 of the speed of the plane, 686 meters. Oh, we already figured out what beta was. 2.29 times 10 to the minus 6th. And we have to square that. So we'll get some time interval finally. I may not be doing these the most organized way today, but try stumbling your way through a few of these things. It's probably instructive, maybe. Okay, I think I get about 3.81 times 10 to the 11th seconds. Let's see. Just for an approximation, 1 year is about 3.16 times 10 to the minus 7th seconds. So it's about pi times 10 to the minus 7th, or 10 to the plus 7th seconds, excuse me. Which is about 12,000 years. Okay, so it's going to be a while. Don't hold your breath waiting for it. And that's how long you'd have to wait. So probably not observable. And relativistic effects just aren't observable for slow speeds at all. So, okay, we've done a few of those. I think we've used the series expansion about 3 times. And I have to review it to myself every time I do it. So that's the way it works. Now, tomorrow we're going to look at some things called the Lorenz transformations and also the Galilean transformations. And with those, we'll be able to develop some formulas for relativistic velocities, velocity transformations, which are kind of interesting. But before we do that, I want to talk about a thought experiment that Einstein had. And I've got this shown in a video that I have at school. And I don't know if I'll have time today to run out to school and pick that up or not. But it's kind of a neat little thought experiment. Einstein had this thought experiment that he wrote about. And he said, imagine that there's a train moving along a track. And then there'd be the engine of the train here. So we'll just imagine that's the engine. Anyway, so it's moving along a track in this direction, along the train tracks. And so got all the tracks on the train track. And there's a couple of light poles that are, or just telegraph poles or something like that, that are along the track. And then there's an observer on the train. So I don't know how to draw that. Anyway, somebody's standing on top of the train, maybe, something like that. And there's an observer standing by the side of the tracks. And 2 bolts of lightning strike these 2 poles. And so bolt of lightning strikes that one, bolt of lightning strikes that one. And they happen in such a way that the observer here has this little box that has mirrors on it that are at 45 degrees, so he can simultaneously see the two poles. And so does the observer on the train. The observer on the train has one of those. And the lightning strikes those things at the instant when this observer on the train is passing this observer on the ground here. The observer on the ground reports that the lightning strikes the two poles simultaneously, so that he sees the flashes of the lightning in the mirrors hitting the two poles at the same instant. Would the observer on the train say that they were simultaneous? And the answer is no, because the train is moving in this direction. It takes time. Now, this is a crazy, extreme example, but it takes time for the lightning that struck these things to travel to here. And while that's happening, the train will have moved forward. And so the lightning from the light from the lightning that strikes this pole won't have as far to go as the light from the lightning that strikes that pole. By the time this observer gets the simultaneous lightning flashes, the observer may be here. And so this distance will end up being, this distance will be shorter than that distance. Now, you'd have to have a really fast train before a human being could actually detect this difference, but you could have some sort of an experimental setup where something would check on this. But the end result is that what is simultaneous for this person is not simultaneous for this person. And you could turn it around and imagine that the lightning strikes the front of the train and the back of the train at the same instant, and this person says it simultaneously. Then how is this person going to observe it? So those are some kind of bizarre things that are predicted by special relativity, and you can actually have them coming out there. Okay, for the last part of today, what I wanted to do, and I'll try to get that film and show it to you tomorrow. It's on I think it's on a DVD that I marked the location on so I could find it. But I wanted to talk about the Galilean transformations. And these are things that are looking at how events will change from one reference frame to another. And so I'm going to have a couple of reference frames, and I'll have a moving reference frame and an at-rest reference frame. And this is related somewhat to the relative velocity things that we looked at fall quarter a little bit. But this will be the S reference frame. This will be X and Y in the S reference frame. Here's the origin of it. And then there will be an S prime frame, which is moving with respect to the S frame. And we'll imagine that this entire reference frame is moving to the right with a speed u, and there will be an X prime coordinate system or coordinate, a Y prime coordinate, and you can imagine a Z and Z prime coordinate that's at right angles to these two, but we can just deal with this. And the two systems are such that at t equals t prime equals 0, the S prime system was right on top of the S system. So we would just say the two systems coincided. I'm not sure that's a word. But I'll say it anyway. I'll just say the two systems coincided, make it a past tense, whether it exists or not. Anyway, that's when the y prime axis would have been right on top of the y axis and so forth. And we can talk about some transformations that are going to occur here. And we'll have a point P. And this point P, I think that's a P, has coordinates x prime, y prime in this particular coordinate system. And so this would be x prime, and then the y coordinate would be y prime. And if I set these things up right, that'll be y prime. And because it's only moving in the x direction, and you could always invent something, a coordinate system that has one of its axes along the direction of motion. So this will be y over here, and we need to figure out what's going on with this. Well, the distance between these two coordinate systems, this will equal ut. Okay, it's the relative speed of this one times however much time has passed. And so we could get something like this. If you were to make transformations from one of these reference systems to the other, things they would always agree on are y and y prime. They would agree on time. They'd say t is equal to t prime. We started the clocks in both of them when the prime system was on top of the other one. And in Galilean transformations, there's no difference as far as the passage of time. And so we wouldn't agree with that. But x is not going to agree with x prime, but we can easily express what it's going to be. X is going to equal x prime plus ut. And so we would be okay with that. And then let's see, what about relative speeds here? Well, I could just take a derivative of both sides of this thing, and I'd get dx dt is going to equal dx prime dt, because t is equal to t prime, and there isn't any difference between the two. Plus, well, when I take the time derivative of this, I just get u. And what I'd end up with is that v sub x, a velocity in the x direction measured in the unprimed system, will equal v sub x prime plus u. And so if this thing happens to be going in the positive direction or something like that, I could do a similar derivative for y as well. But I end up just getting our relative velocity equation, even if I had, excuse me, even if I had a two-dimensional velocity in this thing, I'd get our relative velocity equation. So these are what we might be able to use in Galilean transformations. But one thing that it's based on is that the time is the same in both reference frames. And so we expect the time to run at the same rate in all places, and you could somehow define, you can have a clock in this moving reference system that runs at exactly the same rate as a clock that's in this non-moving reference system. So those things can end up working out. And tomorrow we'll look at what are called the Lorenzian transformations. And they were some things that were worked out by, oh, I think he's one of those people known only by their initials. Although I think it was Alfred Lorentz, but A.E. Lorentz is usually, I think, the way you see his name written. And he worked those out before Einstein published his material on special relativity. And it was to try to somehow explain some experimental observations. And but tomorrow it'll let us look at relative velocities when we start talking about relativistic speeds. And this would be like the light beam that's shot out from a spaceship that's traveling at whatever fraction of the speed of light, seeing why different observers don't come up with a speed faster than that of light. So we'll move into those things tomorrow. So relativistic velocities tomorrow and the Lorentz transformation equations. Okay, let's see, new homework assignment up there. And yeah, I'll get some other stuff posted as well. Oh, let's see, tomorrow afternoon, I'm going to do a demonstration for you of how you can use the electronics you have to have a variable voltage. And it's going to be kind of a tricky lab to do because you've only got 1 meter, and I'm trying to figure out a way to make this work. It may end up having changing the location of the meter a bunch of times for a series of measurements, but that would probably be okay to do. And so I'm thinking probably, maybe 2 or no, probably 3 o'clock would be better. I think I'm giving an astronomy test from about 1 to 2. So anyway, we'll have that going on tomorrow afternoon, but I'll record it so you can watch it at any time. Okay, I'll stop the share here. I think I'm going to set up a thing where you can redo your test as a way to close the gap between the points you earned and the points that were possible. And some of you, it won't be worth your time, but for some of you, it would be. And so I'll do that, and it shouldn't take too long for you to do that, but probably have it be due before this weekend also. So maybe Friday for that as well. So a makeup test assignment, and you'd be using the exact same test that we did instead of having you take a distinct test, which was not a good idea on my part for the last one. But anyway, we'll go ahead and have you do that. So I'll stop here and get to work on, well, the next class is in just a few minutes, but at any rate, be watching for some more stuff this afternoon.